Okay, so good evening, everyone. I hope I'm audible. And if there is any issue with that, you can say in between the meeting. And I request everyone to mute their mics. Okay, so I'll be starting with the session. So, welcome to the first live session for the course Elements of Mechanical Vibration, NOC25-ae17. And I hope you have all gone through the lecture of this week. There were three lectures, which was basically concerned about the overview of why mechanical vibrations are required in case of aerospace engineering and how it is important to study to avoid any kind of resonance condition, to avoid any kind of premature failure, or in order to make the lifespan of any of the machinery high. Okay, so here. So I'll be basically solving some questions in this session so that it will be helpful for you in order to solve the assignment problems. If you have any issue, then you can ask me in between or at the end of the session. That would be better. Okay, so I'll also try to basically give overview of what are some of the basics that are required in order to understand. Okay, coming on to the first question that I have taken, which is to determine the degree of freedom of the following system. So there are two systems that are given. First one is this A, the second one is this B. So when we talk about degrees of freedom, why even it is important that we need to know about the degrees of freedom? So essentially, the first question is, what is a degree of freedom? Although everyone must have been knowing that the degree of freedom is something which is taught to you in, I guess, first or second year of your engineering, but we'll take a brief overview. So degrees of freedom are basically related for any of a mechanical system. So when we try to model a system, right, there are some outputs, there are some inputs. So in order to know that what are the outputs or what are the concerned variables or what are the concerned, positions of my system that I need to study. So how many of them are there? On that basis, we decide what are the degrees of freedom of a system. So if I want to write that what is the degree of freedom, so it is the minimum number of, maybe I should avoid writing here, minimum number of independent coordinates required to determine all positions of all the parts of the system at any time t. Right? So, for example, if I have a spring connected to a mass, and it is oscillating like this, or it is moving in this direction, then what is the degree of freedom? 1. I have one mass which is moving only in one direction. It cannot move in the y direction, it cannot move in the z direction, neither it can rotate, right? So it has only 1 degree of freedom. On the basis of that 1 degree of freedom, I can find out the equation of motion, and then I can solve that equation of motion. Like for this, the equation of motion is going to be mx double dot plus kx is equals to 0. And from here, I can get x as a function of time. So putting on that time, any time t, I can find out that what is the position of m, right? So this is a single degree of freedom system. Now coming on to the first system, which has a spring connected to a mass, somewhat like a piston, and then we have a pendulum which is attached to the center of this mass, right? And it has an angle theta. So see, if I talk about a pendulum, right? If there is a pendulum of mass m like this. So if you see, it is actually moving in the xy plane, right? So we'll think that, okay, if it is moving in the xy plane, we need an x coordinate, we need a y coordinate, and then only we can say that what is going to be the position of the system. But that is not true in this case, because we have a relation, this L. So if I say that this is x and this is y, so we have a relation which says that L square is equals to x square plus y square, right? So by this relation, if I have one value, like either of x or of y, I can evaluate the other on the basis of this relation, because L is known and it is constant. We are considering the rod by which the bob is connected as inextensible, right? So in that case, we have a relation in which we can relate x and y. So we only need one variable, either x or either y, and then we can evaluate the other one, right? So for this case, generally we consider theta, because x and y both can be written in terms of theta. X will be equal to one thing, y will be equal to another thing. Like it's basically L sine theta and L cos theta respectively. So on the basis of that, we can actually write, or we can know what are the coordinates. So when we talk about the pendulum, we consider it as a 1 degree of freedom system. Though it has two coordinates x and y, but we only need one independent coordinate, right? As per the definition, we need the minimum number of independent coordinate, and this system has one minimum number of coordinate that we require, right? So this is a 1 degree of freedom system, and that is why you must have seen we write the equation of motion of a simple pendulum in terms of theta. Okay. So now in this case, if my mass is moving over here like this with x, right? So from that, I'll know the position of that mass. Next comes the bob. Now with this, we'll have a y. Okay, this we can write as capital X. And we have small y, then we have small x. Okay. Apart from knowing this capital X, we need to know the small x and small y as well in order to get the positions or the velocity of this small bob, right? From the capital X, we'll know the velocity and the position of mass m. But for this, we need the small x and small y, right? Now again, since this is sort of a simple pendulum, though my reference point or the pivot point is moving, it is not at a static state. It is moving with time. But the relation of x square plus y square is equals to L square is always going to be true. Why? Because mass is moving only in the horizontal direction and it is constrained in the vertical direction, right? So the change of capital X is going to change the value of small x, but it is not going to change this relation. It is not going to change the length of the string that I have used for suspension of the bob, right? It is not going to change, and it is always going to be in the taut state, or we can say that it's a rod. Let us just not consider it as a string. So this relation is always going to hold true. So in that case, we can take minimum one coordinate for the bob, again theta. So all we need is x and theta in order to find out the position or velocity of the bob or the mass. So this is a 2 degree of freedom system. Okay. Now, if we talk about B. So for B, if you see, it's a cantilever beam. Now, the cantilever beam is actually a continuous system, right? It is a rod which has distributed mass. Okay. Though we can model it as a single degree of freedom system, but it needs lumping of the masses, right? Here, the spring was not having any mass, the rod was not having any mass. The mass was only with the this. This was the only mass, and the bob was the only mass. And it was lumped. Lumped means it was concentrated at a single point. Or you can say that it was concentrated in an area or volume which is very small. Okay, so we consider it as a lumped model. But in this case, which is for a cantilever beam, it is uniformly distributed. The mass is uniformly distributed. So if we go into the structure of it, we'll see that there are infinite number of point masses that constitute the whole cantilever beam, right? There are infinite number of points, right? And then every point has their own coordinates. And every point's movement I need to monitor in order to know the movement of the other nearby points, right? So if I have infinite point masses, I need to have infinite equations to find out that what is going to be the velocity and position corresponding to every mass point. Okay. Okay, I have a question. For the bob, the system is 2 degree of freedom. If we consider M is under single degree of freedom. I'm sorry, I'm not able to get your question. If we consider M, like if you remove this whole bob and rod, then you are asking. Yeah, then it's a single degree of freedom. As I said here I took the example, this one, where a spring was attached with a mass. For this, it is a single degree of freedom system. We have only x coordinate over here, which is required to find out the velocity and the position. I hope it is clear. Okay, so coming on to the cantilever beam. So we have infinite number of point masses, infinite number of coordinates, and there is the minimum number of coordinates required then becomes infinite, and hence this is the infinite degree of freedom system, right? So, on the basis of the degrees of freedom of a system, we actually try to, okay, so on the basis of degrees of freedom, if we have a finite number of degree of freedom, or if we have an infinite number of degrees of freedom. If the number is finite, then we say that it is a lump or discrete model, like the simple pendulum, spring mass system. We can have a spring and a mass system. This is a single degree of freedom. We can have multiple springs and mass, like this is a 3 degree of freedom system. These all come under finite number of degrees of freedom. And we call it as discrete or lump model because the masses are lumped at finite number of points, right? But if there are infinite number of degrees of freedom, the system is essentially continuous continuous or distributed system. As you see over here in lump or discrete model, the mass was concentrated at a point, right? But in case of continuous system, the mass is distributed among all the volume of the system. And we generally consider it is distributed uniformly. So it becomes a continuous or distributed system. Now we know how to deal with a finite number of degrees of freedom system, right? We just have to take out how many number of degrees of freedom we have, that many numbers of coordinate we want to work on, and then that many equations of motion we need to find out. But in case of infinite, we cannot solve infinite equations at a time because we don't even know that what is the exact number. So in that case, we try to convert the infinite degree of freedom system to a finite number of degree of freedom system, right? So that it becomes easy for us. Like, for example, if I have a cantilever beam like this, if a load is applied, it deforms something like this, right? Every point is actually coming down. Like this is now this. Likewise, there are infinite number of points, and this goes on, right? But if I consider it something like this, I can do it. There is no issue, right? I can consider it as a mass and a spring system, which is vertically suspended, right? What I can also do is I can consider multiple springs with a mass, right? But in this case, I am actually taking the system to be something different from what its actual behavior is, right? If I have a continuous system like a cantilever beam and then I model it like a single spring mass system, it is actually not going to give me very accurate results, right? So then I try that I introduce some more numbers of degree of freedom, right? Like for example, I can give maybe 10 or 20 masses in the system, and then I see that how the system behaves. Okay, that way we can do it. Or what I can do is I can just take this system, divide it into maybe 20 parts, and then I try to model every 20 part, and then I relate all those 20 parts because the first part will be related to the second one, second to the third one. If you can see over here, this part will be related to this part. We can define the respective deformations by relating them. Okay, so that is how we can model it. Although we can definitely model it as a continuous system, we can apply the FEM techniques and we can solve it in ANSYS. That is perfectly fine. But if you know that when we deal with a continuous system in FEM, we actually find the partial differential equations, which in case of finite number of degrees of freedom, we get the ordinary differential equation. In this case, we get partial differential equations, and then we solve those partial differential equations in order to get that how the system is going to behave. But the problem while solving these differential equations is that it can be erroneous. If I do not properly solve these differential equations, it can give us results which is just a second. It can give us results. Yeah, it can give us results that are not actually correct. So we generally try to lump it and then solve it so that we can actually get a analytical solution, right? Because for a partial differential equation, getting an analytical solution is very difficult. And I won't say that it's impossible, but it is difficult, very time consuming. And that is why we go to the numerical techniques. However, if we get a closed form solution, we can actually find the solution at every single point of time. Now here where we are not concerned about the nonlinearity of the system, we will find the solution like that only. We will not go into the numerical solution. Okay, so this is what it is. So for a continuously distributed system, there are infinite degrees of freedom because we have infinite point masses. We have infinite mass point, and so we have infinite degree of freedom. So we try to model it as a lump system because it is easier for us. So if I go to this question again, so we have infinite degrees of freedom. Okay, I hope this is clear. So we'll come on to the numerical, but I'd like to mention this one thing that I hope that it is clear to every one of you that why we are actually doing all this. It is very important to understand why we need to do all this rather than doing first. Okay, so if we have a model, we can know how the system is going to behave. If we know how the system is going to behave, then we can know that how should I design my system, what should be the things that must be avoided, and how I can harness the whole capability of my system. Like for example, if I know the natural frequency of my system, I know that what frequency of the excitation I should not be giving to my system to avoid any kind of catastrophic failure, right? To avoid any kind of decrease in the lifespan of my system. Okay, I hope it is clear. So coming on to question number 2, which says that a 0.453 kg mass is attached to a spring and and elongate it by 7.87 mm. The natural frequency of the system is. Okay, so first, what the question says is that there is a spring. Let us say that this length is L. Okay, who is this unknown person? Do you have a name? Or I'll remove you from the
Ma'am, it's
meeting.
me, ma'am. Tejavardhan, ma'am.
Yeah, please change your name in that case.
I'm sure, ma'am. I will change it, ma'am.
Okay. So this has a mass m. So this elongates the system by 7.87 mm. Okay. So see, now this is a model. If you think physically, if I have a spring, if I attach a mass, it is going to oscillate. The oscillation is going to diminish, and after some time, it will come to the equilibrium point, right? But if we look at the model, that is not true. Okay, I'm sorry, I missed your question. What is meant by closed form solution? Okay. Uh, see over here. Just a second, I'll just explain this question. So if I have the equation like kx double dot, sorry, mx double dot plus kx is equals to 0. And if I solve this differential equation, I hope you people must have studied. Okay, okay, fine. Fine if you have understood. Okay, so this elongates by this much. Now, see, this is just a model. Okay, the system should have a damping. It is true because even if I just take a spring and try to attach a mass on it, it is going to oscillate, and after some time, the oscillation is going to diminish. Reason being that we have air drag. Okay, so energy will get dissipated. But this is an ideal case that we are talking about. So let us say that it is at an equilibrium with a spring only. We don't know about the intermediate step as of now because we are just concerned about the natural frequency, and the natural frequency does not depend upon the damping value. Okay. The damping value is only going to control that how much transient we are going to see, up till what time the oscillation is going to happen. Okay. But it does not contribute to anything into the natural frequency of the system. So this is the case. So by the free body diagram, if I see there is this mass m, here is mg, and then there is kx. So we'll have mg is equals to kx, where we have m as 0.453 kg, g is 9.81 meter per second square, and x is 7.87 mm. So if we put it in these equations, we have the equation for k, which is, so if you will calculate this, I've already done the calculation, but you should do the calculation and at least now or after the class, it will come out to be 564.6671 Newton per meter. Okay, so this is the spring constant. Now, the question asks the natural frequency of the system. We know for this kind of system, the natural frequency is given as under root k by m. Okay, and there are various ways of finding out the natural frequency that we will discuss in the further questions. Actually, I've taken many examples in which we'll know about how to evaluate the natural frequency. Anyways, this is what it is. So we have the value of k, we have the value of mass m. So all we need to do is put it into the equation and find out the value. So omega n is going to be under root of 564.6671 divided by 0.453, which will come out to be 35.3059 radian per second. Okay, so option B is going to be the correct option. And I assume that you people know that if we have omega in radian per second, we have frequency in radian per second. And if we want to find it in hertz, which is about rotations per minute, so the relation is something like omega is equals to 2 pi f, where omega is in radians per second and f is in hertz or per second. Okay. Okay. So now we have this. We have a system that we are used to of solving. There is a cylinder, and then it is attached to a spring, and it is kept on a surface which is frictionless, and we consider that there is no slipping. We have no friction and we have no slipping. Okay, and now we have to find the natural frequency, right? So if we now try to see that what are the components. So there is one cylinder, then there is this one spring which is fixed over here, right? This spring has a stiffness K, no mass. This cylinder has a mass M, inertia J naught. It rotates by theta and its radius is R. Okay, and we assume that this spring K extends by X. So if we try to find out that how do we relate this X with theta? Because see, if we want to find the natural frequency, first thing is that we assume, actually we don't have to even assume, okay, assume 1 degree of freedom system. There's only 1 degree of freedom. If there is 1 degree of freedom, there's going to be only one frequency. Okay. As you will study the course more, you'll get to know that with the increase of degrees of freedom, the number of frequencies increases, and yeah, this much is enough as of now. For now, understand that for 1 degree of freedom system, there is going to be only one natural frequency, right? So either I'll have to write the equation in terms of theta, or I'll have to write the equation in terms of x. That is up to me, or that is up to you. Okay. But what is important is to note that if I write equation in terms of theta, it is not like that I don't consider the contribution of the translation, translatory motion. Okay. And if I write the equation in terms of x, I should never ignore the energy which is associated with the rotation theta. I have to consider both. The only thing is that since there is no slipping, I can now relate theta and x with each other. How? So see, earlier the cylinder was something like this here, and then we have this point over here. Okay. This goes to something like this. This was A. Now A comes over here. This was A dash. It was the earlier point. And this angle is nothing but theta, right? This is what is happening. This angle is nothing but theta. Okay. Now, because of this rotation, if you see, its center of mass has also come forward by an amount. And that amount is nothing but x. Okay, I suppose there is some lag with what I'm writing and what is displaying, but it's fine. Okay. So by the rotation theta without slipping, the center of mass has also come forward by the amount x. Okay. Now if we assume that this theta is very small, then I can get a triangle something like this. Okay. Or even if we don't consider that, we already know that we have the relation something like x is equals to r into theta, right? Definitely it is only applicable if theta is very small. For big theta, this will not be applicable. And we are assuming that theta is, here I'll write also, theta is small. I hope this relation, how we have find out is clear, because if we know the relation, everything is done now. Okay. Now, you know, for finding out the natural frequency, there are two ways. First is we know under root k by m. So we find the effective k, we find the effective mass, and then we evaluate. Second is we find the equation of motion, because you know that for a system, the equation of motion is something like this. So if we know omega n square, under root of that will be equal to the natural frequency. So we'll go into the second way, which is first finding the equation of motion. Now, in order to find the equation of motion, there are various ways. For the equation of motion, we can do is use Newton's law, force balance, summation of all the forces is equals to mass into acceleration. We have the energy method, which says that, see, here we have modeled our system in such a way that there is no dissipation. We consider that there is no dissipation. So if there is no dissipation, there is no input of energy we are giving. So it means that whatever the total energy of my system is, it is constant. The only difference is that the energy is being transferred from potential to kinetic energy, kinetic to potential energy. This oscillation is happening every day. Apart from that, the total energy is always constant. So for the energy method, what do? We know that the total energy is constant. Total energy, okay, maybe I should write it. Total energy is constant, which means that if I differentiate with respect to time, the total energy, I'm going to get 0. This is another way of finding out the equation of motion. Then we have principle of virtual work, which says that if a system is in equilibrium, and if I assume that there are works that are being done by the forces that are applied on the system, the summation of all the work is going to be 0 because the system is in equilibrium, it is not moving. So the summation of all the work done by the forces is going to be equal to 0. That is the principle of virtual work. So we'll use the energy method over here because it is easy. At least to me, it seems easy. Now, I need to find the total energy. The total energy is going to be what? Potential energy plus kinetic energy. Now, potential energy, only my spring is going to store the potential energy, right? So the potential energy is going to be, I should take another slide. Only my spring is going to store the potential energy. So potential energy is going to be half k x square, right? Now, if I try to write x in terms of theta, which we already know, it is nothing but half k r square theta square. X is equals to r theta, which we have evaluated earlier. So this is the potential energy. Coming on to the kinetic energy. Kinetic energy will have two parts. One is because of the translation of the cylinder, and second is because of the rotation of the cylinder. Okay, both we should consider. It should not be like that if there is no slipping and if it is rotating and translating and there is no slipping, so if we'll consider only one aspect of energy, it will work. No, you have to consider both because it is rotating as well as translating. Both the things are happening simultaneously and both are taking energy. Okay, so we should consider both. So one is going to be half m x dot square, which is because of the translation. The second is going to be half j theta dot square. Now, since we know x is equals to r theta, x dot is equals to r theta dot. This is going to be half m r square theta dot square plus half j theta dot square. Next, what do we have to do? We have to differentiate the total energy with respect to time, which is going to be d by dt of kinetic energy plus potential energy. Half m r square plus half j theta dot square plus half k x square please switch off your mic and try to avoid switching it on because it creates disturbance in the class. Okay, I should not write it in terms of x, but in terms of theta. If I differentiate it, so what is changing with respect to time? Only theta is changing with respect to time. R is constant, M is constant, J is constant. So we'll just have to differentiate theta. I'll just not write half. It is evident that theta dot square will get differentiated and 2 will get cancelled. So we'll have mr square plus j into theta double dot into theta dot plus k r square theta dot is equals to 0. So you can see theta dot is common. Now we have mr square plus j theta double dot plus k r square theta into theta dot is equals to 0. Now theta dot cannot be equal to 0 because that is not possible. If theta dot is equal to 0, then how the system is going to show motion? Okay, so theta dot cannot be, though it can be 0 at the point where the potential energy is maximum, but it is not always 0. So theta dot will not be equal to 0. So then we get mr square plus j theta double dot plus kr square is equals to 0 theta. Now we got the equation of motion, right? So from this, you can get theta double dot plus kr square divided by mr square plus j into theta is equals to 0. And if we relate it with x double dot plus omega n square, x is equals to 0, we get omega n as k r square. So we get omega n as k r square divided by mr square plus j. Okay, you can see whatever you want to see. Yeah, okay, fine. Okay. Uh, okay, in the question it is J naught, so I should use J naught. Don't get confused. This is J naught only. I hope this is clear. Okay. So this question, the natural frequency of a spring mass system and the mass of the spring is considered is. So we have a spring and then we have a mass. Okay. There's a stiffness K. In this case, my natural frequency is, but here there is an assumption that spring spring is considered to be massless. However, this is not true in physical cases. So now if we consider the mass of the spring, then what is going to happen? So now what is happening is that the end of spring is actually oscillating with a velocity x dot, which is the velocity of the mass, correct? But now since it has a total mass, in that case, every point of mass is going to oscillate with a velocity. and that half m into velocity square of every point is going to give me the kinetic energy, and that points are going to be integrated. Okay, so we consider that the variation of the velocity is linear. Okay, linear means that it is zero at the end, the fixed end of the spring, and it goes to v dot x dot at the point where the mass is attached. Okay, so in that case, if I consider the velocity at any point, like if I take this mass, I cut it into a small strip which has a thickness of y. Okay, for this thickness, I'll have a mass which is what? If I divide this mass by the total length, let us say, which is L, L is the total length of spring. Then for this small area, the mass is going to be m by L into y. Okay, this is the m dash. And its velocity, since we are assuming it is linear, its velocity is going to be what? Its velocity is going to be x dot divided by L into y. Okay, yeah. Actually, mass we can for now consider as m dash. That will be fine. This is the mass for the small element. Okay. Okay. So now we know the velocity. We just have to do the square, right? So it is something going to be like kinetic energy is equals to half m dash into x dot square y l square. Okay. And then we integrate it with respect to dy. Okay. See, this dy, because this small mass m dash is going to be nothing but m by L into dy. It should not be equal to y, because this y is not the thickness, it is actually the length, right? Dot is defined. How y dot? Okay, okay, this is dy, okay, from the distance. So for y dot, we assume that there is a linear variation. Okay, there's a linear variation. With linear variation, we mean that it is something like this, and this. This is x dot. This is L. We have considered point over here, which is y, and here it is y dot. So by the similarity of triangle, we have x dot by L is equals to y dot by y. So this implies y dot, okay, and this implies this. I hope it is clear. Do you have any question? You have raised your hand. Okay, so we'll integrate it from 0 to L. This gives us half m dash will come out, L square will come out, x dot square will come out. Okay. So y square will get integrated with respect to dy, which will give us y cube by 3, and this we will put the limits from 0 to L, will give us nothing but half into m dash by L square x dot square into L cube by 3. Now we can replace m dash by m by L, right? I should write it as ms. Hello? I think that there is some network issue on your side. If you have any question, can you write it? Okay, something like this. So if now we write m dash s, we'll get half. This L square, we'll cut this and there will be 1 only. X dot square by 3, and then we'll have, or we know that m dash s into L is going to be nothing but ms, right? So the kinetic energy for my spring is going to be half ms by 3 into x dot square, right? So for the spring mass system, I had my kinetic energy as half m x dot square. Now there is a addition of half ms by 3 x dot square. So we'll have half m plus s by 3 x dot square. So this is the effective mass. And now if I have the effective mass, I can easily define the, yeah, and now I can easily define the natural frequency, which is going to be nothing but k by m effective under root. Okay, I hope you understand that how we are actually solving this. Coming on to question number 5, wherein we have to determine the equation of motion and the natural frequency for the system shown in the figure. The cylinder has a mass m and there is no slipping between the surface. Okay, so we have a system like this. This is fixed. There is no slipping. This has a mass m. Okay. See, this angle is theta. This movement is theta. And then we have this movement. This is our radius. We have this movement, which is phi. Okay. And this length is capital R. Okay. So the question is that we have to find the equation of motion and the natural frequency. So first things first, how is this thing actually happening? Okay. So this was the tip, okay, which was initially here, something like this. Okay. It then went to that place. Okay. So this point was somewhere here for this system. Okay, I should use another color here. And this point was here earlier. These are the 2 points that we are looking for. This point went here. This point went here. It is oscillating like this. Okay, so now the question is of finding the equation of motion. So we already know the energy method, right? What do we do over there? We find out the kinetic energy, find out the potential energy, evaluate the total energy, differentiate it. Here also, there is no slipping, there is no friction, so there is no dissipation. So the total energy is constant. Okay, it is not changing with respect to time. So if we evaluate the total energy and then we differentiate it, we can find out the equation of motion, right? Just a second. Okay, so to evaluate the total energy, now what do we need? We need to have the kinetic energy, potential energy, right? We have the mass. We know that the cylinder has a mass m. Okay, it is rotating also and its center is moving as well, correct? So if we have the mass m, we can find out the moment of inertia. If you know that for a cylinder, the moment of inertia I is nothing but m r square by 2. Okay, and yeah. So if we try to find out the kinetic energy, so we need two things for that. First is the velocity for translation. Second is the velocity for rotation. Now, the velocity of translation seems fine to me. Okay, it is nothing but what? R into theta. Capital R into theta, right? Because this change from here to here, it is small. So if it is small, then it is going to be nothing but R theta. So if we differentiate that, we get R into theta dot. So kinetic energy due to translation is going to be half m r square theta dot. Okay, sorry. Here it should be capital R square theta dot square. Maybe I should write it over here. Translation velocity r theta dot. Then we have a rotational velocity. Now it would seem easy that maybe I should write, if this is phi, then maybe I should write small r into phi dot square. Oh, sorry, phi dot. And for the kinetic energy, I can do this square. But that is not true in this case. Reason being that in the earlier case, we had a straight surface, right? So the center of the cylinder was actually not rotating about some point. It was just translating. Okay. So its rotation only was contributing towards the rotational kinetic energy. But in this case, the center is rotating about a point capital O, where this is a capital O, right? So we need to define the velocity at the center, okay, with respect to the center of the point, because the center is also moving, relative velocity, okay. So for that, first, from the no slipping, we are going to get a condition. For no slipping, we are going to get a condition which says that r into theta is equals to small r into phi, right? The distance traveled is the same. So in that case, we can get phi with respect to theta as r theta by small r. Okay. And here rotational velocity is going to be relative. So we'll have phi dot minus theta dot. Phi dot we know with respect to uh, no slipping condition, so we can write it as capital R minus small r divided by small r minus 1 into theta dot. Okay. So now from this, I can get my total kinetic energy plus half I square theta dot square. Okay. I hope this is clear. Now we can substitute the value of I that we have calculated. So we are going to get half m r square theta dot square plus half m r square by 2 capital R divided by small. We should just, okay, for now we'll keep it like this only. Theta dot square. This is going to be my kinetic energy. Now we need to evaluate the potential energy. So here the potential energy, there is no spring, so but the potential energy is going to be because of the gravitation, right? So I consider this this line as my reference for evaluating the potential energy. Okay, so if I consider that, okay, why this? We'll consider the center only, this one. Yeah, most convenient, because in this case what we are going to get, we are going to get that at the initial point my potential energy was 0. Okay, now the center goes up by what amount? So let us just take it like earlier it was here, now it has gone here, right? So we need to find this distance in order to find out the potential energy, right? Now we know this is capital R minus small r. Here, this is also capital R minus small r, right? Because this is always going to be constant. It is a circular kind of motion. So how do we find out this? See, if this is theta, this is going to be capital R minus small r into cos theta, right? So this distance is going to be capital R minus small r minus capital R minus small r into cos theta, which is going to be capital R minus small r 1 minus cos theta, right? Now I know the height and I know that gravitational potential is defined as mgh. mgh. So potential energy will be capital R minus small r mg 1 minus cos theta. Now I know the kinetic energy, I know the potential energy. What will I do? I will write the total energy, which is nothing but theta dot square half m r square theta dot square plus half m r square by 2 capital R by small r minus 1 square theta dot square plus capital R minus small r mg 1 minus cos theta. Okay, I have to do nothing, but since the total energy is constant, d of total energy with respect to dt is going to be 0, right? So I can evaluate by differentiating, and we'll get mr square plus mr square by 2 capital R by small r minus 1 square theta double dot into theta dot plus cos theta. Differentiation is going to be minus sine theta. Minus minus will get cancelled. So r minus r mg sine theta into theta dot will be equal to 0. Okay. Now, we already know that since theta is small, sine theta is nearly equal to theta. See, here I would like to emphasize on one thing. Uh, this sine theta is essentially making my system non-linear, which is very important to study when we are talking about the physical system. However, here we are mostly concerned about the linear systems, so we'll use the theta thing, okay? And this theta naught cannot be equal to 0. So we get the equation of motion, something like okay, there's one more thing that I've done wrong here only. Yeah, it should be r minus small r. Yeah, because the center of gravity is actually at a distance of r minus small r from the point O. So we should consider that as well. Yeah, now it's fine. Okay, so if we consider that, then in that case, we'll have m capital R minus small r square. We'll have it like this, right? Now, for the second one, we can send the r square inside so that everything comes in that form. Okay, so then we can get the equation as 2 and plus 1, it is going to be 3. 3m capital R minus small r square divided by 2, yeah, theta double dot plus capital R minus small r mg theta is equals to 0. Now we can again relate it plus capital R minus divided by into 2 by 3 m capital R minus small r whole square to theta is equals to 0. M will get cancelled. This r square will cancel 1 r. So we'll get the final equation as theta double dot plus twice of g divided by 3 times of capital R minus small r. Theta is equals to 0. Again, if we are going to relate it, we are going to get omega n as nothing but twice of g by 3 capital R minus small r under root. Okay, I hope this is clear. So the only difference between this question and the earlier question is that here the center was not rotating with respect to any reference state, right? So here we didn't use the concept of relative velocity, but here we did use. Okay. So coming on to question number 6, which asks that a spring mass system has stiffness K1 and mass M1. Okay, we'll make it first. We have a spring mass system. There's a mass M1, K1. If a second spring K2 is added in series with the first, and the natural frequency changes to half of the earlier, then K2 in terms of K1 is. Okay. So this is transformed into some other system such that this K1 now has a K2 with it, and then there is mass M1. K1, K2. Okay. This had a frequency of, and this will have a frequency of KEQ by M1. This is F1. We have, okay, we'll let it as F1, F2 to avoid any kind of confusion. So we have that the natural frequency changes to half of the earlier. F2 is equals to 1 by 2 of F1. So we need to find K2. Okay. So see, firstly, if two spring are in series, okay, how do we deal with it? See, if I have this spring first, K2, here I have mg, and here I have K2 into whatever x is. Anyways, if I assume it is x2, K2 into x2. See, at every point, what is going to happen? At every point, the force is going to be balanced. Okay, so K2 into x2 will be equal to mg. Similarly, K1 x1 will also be equal to mg. Okay, which means K1 into x2, K1 into x1 will be equal to K2 into x2. Okay, so okay, this is fine. But another equation also says that x1 plus x2 is equals to, let us say, x. Then kx is equals to mg, keq. Okay, now from here I can get x2 as mg by k2, x1 as mg by k1, and if I substitute these two in this, what am I going to get? I'm going to get keq x is equals to mg by k1 plus mg by k2. And from here I'm going to get x is equals to mg by keq, which is equals to mg by keq. Mg will get cancelled, so we get 1 by k equivalent is equals to 1 by k1 plus k2. If we solve this, we get keq is equals to k1 k2 by k1 plus k2. Fine. Okay. Now, since we have the equation of keq in terms of k1 and k2 now, I can use that and put it in this relation, right? Now I know that my F2 is k1 plus k2 divided by k1 k2 mg, and this is equals to nothing but half of under root of k1 by m1, not mg, m1. Okay, sorry. Yeah, like this. K1 will get cancelled with K1, M1 will get cancelled with M1. So we'll get squaring on both sides. K2 is equals to 4 times of K2 is equals to K1 plus K2. 3K2 is equals to K1, which implies K2 is equals to K1 by 3. Okay. So this tells us that if we add one more one more spring along with the another spring, earlier spring, of a stiffness one third of the earlier spring, then the frequency is going to be half. Okay, with respect to the first one. Yeah, we got the answer. This is going to be the answer. These kind of a things are really helpful when we try to design the system such that we can tune the natural frequency of the system. For example, I had a system which had a frequency of, let us say, 20 hertz. Okay, but now I have to give it, I am forced to give it a input excitation with a frequency of 20 hertz only. So it is going to operate in resonance, which I don't want. So then what will I do? I will introduce another spring system into my system that will reduce half, like it will make the natural frequency half. So in that case, I have no problem now, because now even if I give it 20 hertz, but it is what? It is twice of the actually the resonance condition, right? So this is basically use these kind of things when we want to tune the frequency of a system in order to avoid resonance conditions. Anamika, do you have any question?
Yes, ma'am. Actually, I saw one question yesterday in the recall questions which are given on the portal. So,
Recall questions as in?
actually, I have taken the Swayam course of this subject, and in one of the lecture, there were recall question at the end of the lecture. So, in
Okay,
that,
okay,
so the question was that if the free vibration response of a single degree of freedom system to some initial condition is given by x uh, as a function of t equals to 1.5 sine 5t plus theta, if theta is equals to 0, we must be that must be the correct initial condition from the following, and the options were only initial displacement, only initial velocity, no initial displacement and velocity, both initial displacement and velocity.
okay,
So in this question, I got the answer as only initial displacement, but the correct was only initial velocity.
okay,
So when I saw the solution, like how it is happening, so I got that how we are getting the initial velocity part, but there was another idea also for this question. Like we have the theta as tan inverse of initial velocity divided by initial displacement into omega n, right?
yeah.
If in that, if we see if the theta is 0, that means tan inverse of the bracket part will be 0, and if that bracket part is 0, then v naught should be 0, which is the initial velocity. Then why are we saying that initial displacement is not there?
Sorry, I'm not able to get your question, Anamika, as of now. So, I think what you're trying to say is that on the basis of theta, the phase angle, there was a question that was asking that what is the initial condition, right?
Yes, yes.
So you're telling me that we have tan theta is equals to. Okay, so can you mail me this? Because I have only almost half an hour and I have to complete five, six more questions.
Sure, ma'am. Can you just tell your email?
Yeah, it's, wait, I'll write it over here. Rashi underscore 2121 ME13 at the rate IITP.ac.in. IITP. It's fine.
Is it me before
Yeah, it's
13?
ME
Okay.
2121 ME13.
Okay, ma'am. Thank you.
Okay, please send me a mail. I'll respond you by tomorrow morning. Okay. So for question number 7, we have less time now, so I'll try that we can complete it on time. See, we have a system like this. There is a rod like this. We have a spring. This is fixed. Force is applied over here, not at the center, but at some displacement. This is assumed as L1. This is L2. This is the force F. We have K2. We have K1. And this is assumed as X. Okay. See, the first thing that comes to our mind is that Since the force is not applied in the center, the rod is not going to be horizontal after displacement. The force is more on this side, this will displace more, that side will not displace that much. We assume that the configuration is something like this. This is x1, this is x2, this is x. Okay. So if I draw a line over here, dotted line will be better. So by similarity of triangle, what do I get? I get this as x2 minus x1. I get this as x minus x1. This is L1. This is L1 plus L2. So we have x minus x1 by L1 plus L2 is equals to x2 minus x1 by, okay, this is L1 only. Okay, this is the relation that we are going to get. This will give x1 plus L1, x2 minus x1 divided by L1 plus L2. Okay, if we break the upper bracket, we are going to get L2 by L1 plus L2 into x1 plus L1 by L1 plus L2 into x2. Okay, this relation we are going to use further. For now, this is the relation where we can write x in terms of x1 and x2. Okay, now coming on to the force balance. If you remember that we can do two things. We can balance the force, we can balance the moment. Okay, so if we balance the force, what am I going to get? I'll get k1 x1 plus k2 x2 is equals to F, right? And then by balancing of the moment, we'll get K1 X1 L1 is equals to K2 X2 L2. Because if you'll see over here, this spring is going to apply a force in the upward direction. This is also going to apply the force in the upward direction. If we take the center as this is going to create a anti-clockwise. This is going to create a clockwise moment. So the opposite moments are going to balance each other. Okay. So from here, what do I get? From here, I can write x1 as k2 x2 L2 divided by k1 L1, right? And then we can substitute this in this, right? So what we are going to get from that? We are going to get k1 into k2 x2 L2 by k1 L1 plus k2 x2 is equals to F, right? K1 will get cancelled. This implies K2 X2 by L1, okay, K2 X2 into L2 by L1 plus 1 is equals to F. So we'll get X2 as F L1 by L1 plus L2 into K2. What did I get? I got X2 in terms of F L K2. Okay. Similarly, I can get X1 also in terms of F L1 L2 and K1. Right? So if you'll substitute it, I'll not get into that. You'll get x1 as f L2 by L1 plus L2 into K1. substitute this and this into this. Okay, so then what are we going to get? We are going to get L2 is L2, x is equals to L2 by L1 plus L2 into x1, which is F into L2 by L1 plus L2 into K1 plus L1 by L1 plus L2 into F L1 by L1 plus L2 into K2, right? So this will give us x is equals to F L1 square by L1 plus L2 whole square into 1 by K1 plus F L1 square L1 plus L2. Okay, no, this is L2 square, no? L1 square is square into 1 by K2. This will give us F 1 plus L2 square into L2 square by K1 plus L1 square by K2. This will finally give us F by L1 plus L2 square into K2 L1 square, sorry, K2 L2 square plus K1 L1 square divided by K1 K2. This will be equal to X. And we know that K is nothing but F by X, right? We know that F is equals to Kx, right? So from this relation we have F, we have X. So this that is remaining is nothing but, this is nothing but 1 by K, correct? Where K is nothing but the equivalent thing. Okay. So from here we can write Keq divided by F K2 L2 square plus K1 L1 square. Okay, this is the final answer. So coming on to question number 8. See, here we have a torsional system. Okay, so how do we deal with a torsional system? See, the first thing is that in case of torsion, if
Ma'am,
they are, yes,
ma'am, in the previous question, I couldn't see the final answer, ma'am.
this is the final answer.
Yes, yes, ma'am.
Okay, is it fine?
Yes, ma'am. Thank you, ma'am.
Okay. So see, for a torsional system, what happens is that if there are three rods in series, okay, so what happens is if one rod rotates by theta 1, another rotates by theta 2, third rotates by theta 3, then the total rotation is theta 1 plus theta 2 plus theta 3. All the three are not going to deform by the same amount, right? If this you must have been gone through in your strength of materials course. Okay, so for K1, K2, K3, which are the torsional stiffnesses, we can just find the equivalent. Now, because they are in series, we know that for series, we have 1 by K equivalent is equals to 1 by K1 plus 1 by K2 plus 1 by K3. So we'll get the K equivalent as nothing but K1, K2, K3 divided by K1, K2 plus K2, K3 plus K3, K1. This is my equivalent spring constant. Okay. Now, evaluating the remaining. See, K1, K2, K3, for now we'll assume that it is KEQ. Okay. And K4. If you'll see, they are both in parallel. Why I'm saying? Because if this disk is rotating by theta, then the KEQ and K4 elements are also going to rotate by theta. And this happens only in the case of parallel spring arrangement. You know parallel spring arrangement? We have like this and like this, and then we have a mass M. So the deformation in both the springs are the same, which is X and X. Okay, I hope it is clear. So K4 and KEQ are in series. So we'll have K4 plus KEQ, something like this. Now, coming on to K3, K5 and K6. How do we deal with K5 and K6? Because these are linear springs and it is a torsional system. So either we change the torsional system into translation. The best way is, since we have four springs already in the torsional state, it is better that we evaluate the working of K5 and K6 in the torsional way only. Okay. So if you look at this thing, what is happening? If we look at the top view, we have a disk like this, which has a center over here, and it has a radius r. Okay, so there are two springs. No, these questions will not be posted anywhere, but this video, okay, maybe you'll get the presentation also, no? Yeah. Tomorrow morning, people must have got the link to the Excel sheet, or maybe if you log in the NPTEL portal, you are going to get the link for the Google Sheet, wherein if you click on the YouTube link, this whole session, I'm recording it, so I will post it tomorrow morning on YouTube, and you'll get the link from that Excel sheet. And there also you'll get a drive link. In that drive link, you can go through the PPT. This PPT that I'm working on, I'll share it over there. Okay, so something like this. Okay, here we have K6, K5. Now, what is happening is that this is rotating by theta. This is rotating by theta. Okay, so for this spring, what is going to happen? It was initially here. Now it will go something like from this point to this point. But see, here we'll consider that the variation is small. So for the small variation, the uh, movement of the spring, it is going to be linear. So for K6, it will get compressed, something like this. It will get compressed by what? By amount this. And how much is this amount? Nothing but r theta, right? This is nothing but r theta because theta is small. Similarly, this is for K6. If I look for K5, which is initially like this, it will get elongated from here to here. And how much is this amount? R theta. So K6, there is compression. K5, there is extension. Right. So if we talk about uh, the energy which is stored, I can write it in terms of theta, right? I can write it in terms of theta. So now if I try to write the total potential energy, okay? Because if I write the total potential energy, I can evaluate K final equivalent. So the total potential energy is going to be half KEQ theta square plus half K4 theta square, right? Because this K1, K2, K3, and K4 are torsional stiffnesses. I'll write it also. Torsional stiffness are defined in terms of per unit uh, angular variation. These are torsional stiffness. Okay, so K4 into theta square. Then we have K5 and K6, wherein we have half K5, the total movement. Now K5 and K6 are not torsional stiffnesses, they are spring stiffnesses. So it is defined in terms of per unit your movement position. K5 into R square theta square plus half K6 R square theta square, right? If we now add it, half theta square KQ plus K4 plus K5 R square plus K6 R square. This is going to be nothing but my K effective. So finally, my K effective turns out to be K1, K2, K3, K1, K2, K2, K3, K3, K1 plus K4 plus R square, K5, K6. This is my effective spring constant. I hope it is clear. Okay. Coming on to question number 9, we have okay, we have 20 minutes. Okay. So now coming on to some, up till now we were actually using lumped models, right? And we were doing questions which were related to finding out the natural frequencies or the effective stiffness. In this case, the question says that a uniform rod of length L, cross-sectional area A, and Young's modulus E has a mass m at the end. Okay, there's a rod, there is a mass m at the end, and it is fixed. It is subjected to a tensile force F in the axial direction, as shown in figure, which is made by me. Okay, this is the force F. The natural frequency of the system, when the system is modeled as a 1 degree of freedom system, is, we have to consider the mass of the rod negligible, which means that we have a mass, lumped mass, and the rod will work only as a spring, right? Now we have to model it as a 1 degree of freedom system. So how are we going to model it? Simple. A spring, a massless spring, and a mass m, the force F. Okay. So for the natural frequency, see, I know that the equation of motion is going to be m x double dot plus kx is equals to F. M I know, but what about K? I don't have any idea about K. Okay. So, if you remember that in case of such kind of a system, if I write delta, where delta is the change in length of rod, it is going to be nothing but epsilon into L, which where this is what? This is the strain, which is nothing but delta by L. I can write it like that. Now this is a strain. So we know by Hooke's law that stress is equals to directly proportional to, yeah, your stress is directly proportional to strain, and this constant of proportionality turns out to be the Young's modulus, right? So now I can write this as into L. Okay. Sigma is what? Stress. Sigma is stress, which is what? Force by cross-sectional area. If I'll put it over here, I'll get this as force into L by A into E. Okay. So from here we get the relation F is equals to A E by L into delta, force deformation. So if I model it as a spring, in which I relate it as F is equals to K delta. So my K is nothing but A E by L, right? So now I know K. So in this case, my natural frequency of the system is going to be A E by L into mass M under root. See, although this is not true if I take a rod and I fix a mass M, because that rod is going to have its own mass, right? So this is true only if we model it as a 1 degree of freedom system. Okay. And for modeling, it's my choice whether I want to model it as a 1 degree of freedom system, whether I want to model it as a 2 degree of freedom system, or as a continuous system. Okay. But this is the first approach, the simplest approach. Okay. Okay, there was no point of giving the options over here. Yeah. So, okay. So we have to consider the same configuration. Consider that consider the rod as a cantilever beam. Now the natural frequency of the system when the system is modeled as a 1 degree of freedom systems. We consider the again same system. But this time we are looking into the lateral movement, this movement of the system. Okay. Earlier it was the axial movement. Now we are applying a force like this P. Okay. So this is a cantilever beam, and in strength of materials, you people must have studied that in this case, the deflection X, which is the deflection, when for a cantilever beam, a load is applied at the end, the deflection is nothing but P L cube by 3 EI, where EI is nothing but the flexural rigidity of the rod. Okay, E is the Young's modulus and I is the moment of inertia that you people know. So in this case, now if I relate it, what do I get? I get P is equals to 3 EI by L cube into X, where X is the deflection. This is K, right? So then omega n is under root of 3 EI by L cube into m. This is the natural frequency. Now you see for the above case, for the question number 9 case and question number 10 case, though my system is the same, right? But in one case we are looking into the axial movement, and in the other case we are looking into the lateral movement. And because of that only, there is a lot of difference in between the natural frequency of the system, right? Okay, now coming on to question number 11. Yeah. So we have this system where the diameter of the rod is 0.5 centimeter and the length is 2 meter. The wheel makes 10 oscillations in 30.2 seconds when an angular displacement is given. Okay, I guess there was some problem with the question editing. Oh, I think we had to find out the, yeah, let me just check.
Ma'am,
Yes.
ma'am, in the previous question, what is that EA, ma'am? It means flexural rigidity of the rod. What does it mean, ma'am, the term flexural rigidity?
See, this is something which is related actually to the strength of the materials. Okay,
Okay, ma'am.
so you should refer to a strength of material book, then you'll get to know that what is meant by the flexural rigidity. Okay.
Yes, ma'am. Whether the formula X deflection formula is a ready-made formula for cantilever beam applying with the load M.
Okay, so have you studied strength of materials till now?
Yes, ma'am.
Yeah, so in that you must have studied, na, for the beams,
Yes, ma'am.
shear force and bending moment diagrams and everything. So there,
In my college, it is now in the starting stage, ma'am. I am in third semester now, ma'am.
okay, so do one thing, refer to S.S. Rao, mechanical vibration. There you'll
Yes,
get
ma'am.
the formula already written. Okay, so for these cases, we usually take up the formula and use it because they're already derived in strength of materials with a very long procedure. Okay,
Okay, ma'am.
okay.
Yes,
So
ma'am.
you refer to S.S. Rao, you'll get the equation.
Yes, ma'am.
Yeah, so here we had to find out actually, find find the moment of inertia of the wheel. Okay, we have to find the moment of inertia of the wheel, which is this J. Okay. See, first thing that is given to us is that the wheel makes 10 oscillations in 30.2 seconds. Okay. From this, we can calculate the frequency, natural frequency. Okay. 10 oscillations in 30.2 seconds. So one oscillation in 3.02 second. Okay. Or maybe we should do it something like this, that in 1 second it does 10 divided by 30.2 oscillation, because that is what frequency in hertz mean, right? How many oscillations or how many rotations are done in a second. Okay. Sorry. So if this is f, which is the frequency in hertz, we can find omega n as 2 pi f, which is equals to 2 pi into 10 by 30.2, which will come out as 2.081 radians per second. So we are already done with finding out the omega n. Now what do we want? We know that omega n is going to be nothing but something related to under root k by m. Okay. But this is a torsional system. Okay. So I have to find the torsional stiffness. And instead of mass, I'll be using the moment of inertia, which is J, which I have to find out only in the question. So the one thing that I have to find out is the stiffness. J is already the thing that I have to find, and stiffness is something that I need to find out in order to get J. Now see, for the rod, we have to find out the torsional stiffness, and this is related to the equation which is again related to the strength of materials, G, J of rod by L. G, J by L, where G is the shear modulus, Jr is the polar moment of inertia of rod, L is the length of rod. And all these values are given or I'll have to evaluate. I think I've not written in the question. Just take G as 8 into 10 to the power 9 Newton per meter square. Take Jr as, we have to evaluate it. It is pi d by 4, 32. Yeah, so pi by 32. D is 0.5. We'll change it into meters. 100 whole square. This will turn out to be, so I've done the calculation earlier only. Yeah, it will turn out to be 0.006136 10 to the power minus 8 meter to the power 4. Okay, I'll add one more slide. L we already know it is given, right? L, it is 2 meter. So I'll put it in this equation. K is equals to G JR by L, which is A22 10 to the power 9, 18 to 10 to the power 9, 0.006136 into 10 to the power minus 8 divided by 2. This will turn out to be 2.455 Newton meter per radian. Okay, so we have evaluated K, which we needed to find out. And we know that omega n is nothing but under root of K divided by J. Omega n we know from the question, K we have evaluated, we have to find out J, which is asked in the question. So we'll get J is equals to K by omega n square, which will be 2.455 divided by omega n, which was 2.081. 2.081 square, and this will give us J Okay, why is this not working? Yeah, it will come out to be 0.567 kg meter square. This is the final answer. Okay. Okay, we have 2 questions remaining and we have only 5 minutes. Okay, I'll discuss this question because you have a question which is related to this in your assignment problem, and we'll skip the last question as of now. Okay, see, here you have a system wherein the bar has a moment of inertia J naught and it has a mass m as well. And we have to find out the natural frequency of the system. Okay, see, first thing first, there is the uh, pivot point is actually at a distance c from the center of gravity. Okay, so okay, and the center of gravity is over here. This is A, this is B. Here we have mg. This distance is c. Okay, for now we have P1, P2. Okay, P1, P2 is nothing but the support forces. Okay, we are not giving any kind of perturbation to the system as of now. So what is going to happen? There is a force P1, there is a force P2, and then there is mg. So there are two things that needs to be balanced. First is the moment balancing, and second is the force balancing. So we have mg is equals to P1 plus P2, right? Then we have another equation that says that if pivot point, if I take as my reference point, and if I have P1, I have P2, and then I have mg. It is rotating my system in this direction, this is rotating in this direction, and this is rotating in this direction. So what do I have? If I consider that clockwise as positive, okay, we have P1A minus mg c, and then no, it will be plus, right? Because it is again in the clockwise direction, and minus P2 into B. This is equal to 0. This is by the equilibrium condition. Mind it, this is happening, this equilibrium equation is required only and only because my center of gravity is actually different from the pivotal point. If my pivot was in the center, I don't need to find this, okay? Because everything will get balanced by the equal points, okay? Because there is a mass which is not acting in the center, that is the issue. If it would have been in the center, then it would have been a very easy problem. Okay, now this is fine. Now I give it a perturbation like it is shown in the picture by theta. So what will happen? This was how it was earlier. Now it is something like this, where this is theta. We have this, we have this. This is what? This will be B theta. This will be A theta, right? So now if I evaluate the moment so that I can get the equation of motion, and this is going to be nothing but J naught theta double dot. So I get that J naught theta double dot is going to be equal to summation of all the moments about O, which will be nothing but, see, here we have two things. P1 was already acting, P1 was already acting in the upward direction, right? Now, since the spring has elongated, because of that elongation, the spring is going to stretch itself. So this P1 will get replaced by minus of A theta. The total deformation over here is going to be this. While here there was already P2 in the upward direction, right? And now since the spring has compressed, this P2 will get increased by plus B theta, definitely multiplied with K. Okay, so these are the forces that are going to be acted, and mg is always going to act in the downward direction. Now, if I evaluate the moments, what is it going to be? I'll have J naught theta double dot is equal to summation of all the moments about O. This is O. I'll have P1 minus K A theta into A, positive in the clockwise direction. I'll write it clockwise, positive, anti-clockwise, negative. Okay, then plus mg into what? Mg into c theta. This is what? This is c theta. C theta. Or mg is going to have a c theta, or is this going to be just mg into c? No, why c theta? Sorry. It is going to be c. It is already acting in this. We know it. It is perpendicular, so only this arm distance will be multiplied. Okay. And then we have P2, which is acting in the upward direction. This is acting in the upward direction, so anti-clockwise. Minus of P2 plus K B theta into B, right? Now, if I look into equation 2 by using equation 2, we know what? We know that P1 into A plus mgc P2 into B is what? 0. So we'll eliminate this. So what do we get? Now we get J naught theta double dot is equals to minus of K A square theta minus of K B square theta. This will be J naught theta double dot plus K A square plus B square theta is equals to 0. So this will give us theta double dot K by J naught A square plus B square is equals to 0. So we have omega n as nothing but under root of K A square plus B square divided by J naught. Okay, this is going to be the natural frequency. Yeah. So this is going to be the natural, there was no point of giving these options. So this is going to be the natural frequency of the system, correct? Okay, we are already 4 minutes more. So we'll end this class here. There's one more question which is remaining that I'll discuss in the uh, next live session next week. So do you have any questions, or we'll end the live session?
Ma'am,
Yes,
ma'am, where could I get the drive file you told, no, ma'am?
which one?
For our class, that entire those PDF like structure.
PDF structure as of you're talking about the links of the YouTube video and everything.
Yes, ma'am. Those videos were very old videos, ma'am. I saw them, but it was like it was taken in last year, the last before year.
No, no. Where
Why?
did you have you guys logged in like this NPTEL platform, Swayam platform?
Yes, ma'am.
So where you get the assignments, there didn't you see the live session link and everything?
Yes, ma'am. But I saw that in the previous week with things and all, it was old videos only, no, ma'am.
No, no, now it will get updated. Don't worry. When you log in into Swayamna, you'll check there you will get the link for live sessions. Okay, just click on the
Yes,
tabs and check, then you can get. Or if you don't get, just mail me. I have given my email ID. You just mail me, and then I can share the link with you, or how you can go through the link.
yes, ma'am. Like from tomorrow, will there be daily live classes, ma'am?
No, no, no. Every Tuesday, 6 to 8.
Okay, ma'am. Yes, ma'am.
Okay, then we'll end the live session. If you people still have any questions, we can discuss in the next live session. Okay, thank you for joining.